All right, guys. So in this video, we're going to be starting off chapter 7. All right. So we're going to be looking at what was the average for the chapter 6 test. So this is the first video for section 7.1. It says, how did the chapter 6 test go? Today, we will be taking a sample from a population. We will use the average from that sample to estimate the average for the population. Now, it says, let's start with a very simple example. My fifth period is very small. There were only 4 students who took the Chapter 6 test. Their scores were 60, 70, 80, and 90. And it says on question 1, make a dot plot of the population distribution. So I'm just going to make a number line. All right. Okay, since we only got 4 numbers, 60, 70, 80, and 90. All right, and then I'm going to put a dot for each one of these scores. Okay, and don't forget, whenever you're making a graph, always make sure to label it, give it a title. It's we're going to have this one called population distribution. Of scores. Okay, now each one of these dots represents one person, one individual from that population. Okay, so this one that I just circled here is one individual with a score of 90. Okay, so depending on where it lands on the number line tells you what their score was. All right, now it's very easy to look at the population of size 4. Okay, but typically you're not looking at just a population of size 4. You're looking at populations in the thousands, right? So like, for example, what if we wanted to take data based on every single student that took the Chapter 6 test across the entire U.S.? That could be upwards of 5 or even 10,000 people, right? So typically, you're not going to take an entire population, but what you could do is you could actually take a sample of that population. You can take samples of different sizes, but you typically don't know your entire population's value, like each of the individuals in the population. So what we can do is we can take a sample and try and use that to represent a population. All right, so here in question 2, it says, take a sample of any 2 of the scores. Find the mean of your sample. All right, so we've got all the numbers here, 60, 70, 80, and 90. You can use a random number generator on your calculator or really any other way you want to do it. But let's say, for example, I take a sample and I get numbers 60 and 70. All right, so if I average those together, I'm going to get an average of 65. All right, so this sample right here is a 65 average. This is what's known as our sample mean. All right, and we typically use the symbol X bar to represent a sample mean. Okay, number 3 says, figure out all of the possible samples of size 2. Calculate a sample mean for each sample of 2. So since I've got 4 people that took this test, I'm going to list out all the possible samples of size 2. So I could have randomly sampled. We already got 60 and 70. They had a sample mean of 65. Then we've got 60 and 80. That's a sample mean of 70. We've got 60 and 90. That's a sample mean of 75. We've got 70 and 80. That has a sample mean also of 75. We've got 70 and 90. That's a sample mean of 80. And then last we've got 80 and 90. That's a sample mean of 85. All right. So each one of these values, okay, each one of these values right here, 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 all these sample means right here, these are what are known as statistics. Okay. These are statistics. And what a statistic is, it's just a number that represents a sample. So each and every one of these numbers that I've highlighted, these sample means, these are statistics. And now it's asking us to create a dot plot for those numbers in number 3, or question 3. So if I create a distribution here, I've got numbers ranging from 65 all the way up to 85. So I'm just going to go 65, 70, 75, 80, 85. All right, and so I'm going to put a dot for each one of those. So I've got 165, 170, I got two 75s, an 80, and an 85. All right, and then don't forget, we got to label it, got to give it a title. So this is a sampling distribution of X bar. All right. And so each one of these dots represents one sample, all right, one sample mean. So for example, this one right here is one sample mean of 85. All right, so instead of an individual, it's a sample mean, right? Now, question 5 says, what is the mean of the population? Label this on the dot plot above. So this is where samples are very helpful, all right? So it is very easy to find the population mean here, all right? We've only got 4 people in this entire population, and 60, 70, 80, 90. It's really easy to find the mean of that. But like we were saying, typically you don't have a population that small. Populations are in the hundreds or thousands or tens or hundreds of thousands, right? So if we were to try and estimate the population mean based off this sample distribution, we might say that the population mean is right around maybe like here. It might be 75, right? So we use mu as our population mean. We estimate it to be 75 based on this graph, this sampling distribution. But if we were to actually calculate it, okay, so we would do 60 plus 70 plus 80 plus 90 divided by 4. Those are all of our individuals in the population. We would get 75 as our population mean, all right? And we usually use mu as our representation for that, or symbol, okay? So this is our population mean. Okay, this is what's known as a parameter. Okay, so instead of a statistic, this is what's known as a parameter. All right, a parameter is just a number that represents the population. All right, so it's a number that represents everybody in a population. And you can see on question 4, we had a sampling distribution, and it actually accurately represented what the population mean was going to be. We estimated based on the graph it would be 75, and then when we calculated the population mean, it actually was 75. So what that means is that this sampling distribution is unbiased. All right, it is a good unbiased estimator of the population. All right, so there's 2 different types of sampling distributions. There is biased and unbiased. So I'm going to write this out. A statistic is an unbiased estimator if the mean of the sampling distribution equals the parameter. Okay, so in the example here we have number 4, this sampling distribution is an unbiased estimator because it accurately represents the true population mean. All right, so a couple takeaways, important ideas. What is a sampling distribution day one? So number one, parameter and statistic. So parameter is just a number that represents the population. And a statistic, or sorry, excuse me. I was right the first time. Statistic is a number that represents the sample. Okay, and so we actually have different symbols to help represent these values. Okay, depending on what type of values you're looking at, we're going to have, you have symbols that represent parameters and statistics for means, proportions, and standard deviations. So if I write this out, parameter, I'm going to make a little table here, statistic, mean, proportion, and standard deviation. And so the symbol we use for a population mean is mu. If we're looking at a sample, it's going to be x bar. It's like we did in this example here. If you're looking at a proportion, like a fraction, population proportion, we use capital P. For a statistic or a sample, we use p hat, p with a little arrow on top. And for standard deviation, the population, we use sigma. And for a statistic, we just use a lowercase s. All right, so that's first thing. Next thing I want to look at is a sampling distribution. Okay, so a sampling distribution just shows the statistic found in all possible samples of size n. So it shows the statistics found in all possible samples of size n. All right, so if we go back up to question 4 really quick, we had a sampling distribution of x bar here. These were of size 2. This one is a sampling distribution because it shows all possible examples of size 2. All right, and then the last thing, number 3, kind of has 2 parts to it, but the first thing is that a statistic is an unbiased estimator if the mean of the sampling distribution equals the parameter. Okay, so in our example, we had a sampling distribution that looked pretty symmetric, right? And we had a population parameter, mu, right there in the center, and they both represented the same value. That would be unbiased. All right. But for example, let's say that our distribution looked the same, right? It looked something like this, but then our population parameter was way up here, right? The true population mean was up there. That would be biased, okay? And there's a bunch of different ways or reasons why that might be. Might be because you miscalculated your samples, you left people out when you were doing random sampling, you could have miscalculated, something like that, whatever the reason might be. But if it doesn't accurately represent the population, then it will be biased in some manner, all right? So that was the first part. The last part, okay, when increasing sample size, variability decreases. Okay? In other words, as sample size goes up, variability goes down. Okay? And so what I mean by that is, I'm going to go back one more time. We have a sampling distribution for samples of size 2 right here on question 4, right? Now, if we took, instead of sample size 2, okay, like we did here, what if we took samples of size 1? Well, we would have numbers ranging from 60 to 90, right? So our numbers would actually go down further down and farther up on our sampling distribution. But we took size 2, and that kind of made it a little bit smaller to 65 to 85. If we took a size 3, it might be somewhere around 70 to 80. And if we took a sample of size 4, which is actually the entire population, we would only have one dot sitting on 75, just like our population mean, all right? So as we increase our sample size, the variability, the amount that it spreads out, decreases. All right, so last thing is check your understanding. It says the James family has 5 children. Jocelyn, which is age 8, Alice, which is age 8, Michael, age 14, Erica, age 16, and Sarah, age 18. It says complete the table by listing the 10 possible samples of size n equals 2 from this population and calculate the sample mean age for each sample. The first column is completed for you. So they already took Jocelyn and Alice. I'm actually going to shorten these names. Jocelyn is J, Alice is A, Michael is M, Erica is E, and Sarah is S. And so I'm going to take samples of size 2. JA has already been done. Then we've got JM, JE, JS, and then we've got AM, AE, AS, and then we've got ME, MS, and then ES. All right. And so if I take all of their ages and average them together, I'm going to get 11, 12, 13, 11, 12, 13, and then 15, 16, and 17. And part B says, create a sampling distribution of the mean age of samples of size 2. So I'm going to create a number line. I've got numbers ranging from 8 all the way up to 17. So I'm just going to make a tick mark for each one of those. So I've got 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Okay, and then I'm going to put a dot for each one. So I've got 1 dot on 8, and then 2 on 11, 12, and 13. And then 15, 16, and 17. And last thing I got to do is give it a title. So this represents a sampling distribution of X bar. All right. And now it says, part C says, what is the mean of the sampling distribution of the sample mean and what is the mean of the population? So we're going to have to calculate two different means here, a mean of this sampling distribution and then also a mean for the population. so all 5 kids together. And so if I do the sampling distribution, I'm going to have mu sub x bar, okay? And all I'm doing is I'm just adding up all of these numbers and dividing it by however many I have. I've got 10 dots, so I'm going to have 8 plus 11 plus 11 plus all the way up to plus 17, because that's my highest, and divided by 10, because that's how many dots I've got, and my final answer is 12.8. And now if I do it for the population, I'm going to have 8 plus 8 plus 14 plus 16 plus 18 divided by 5. And I'm also going to get 12.8. So both of these numbers are exactly the same. Got 12.8 for the samples, 12.8 for the population. And it's part D says, is the sample mean an unbiased estimator of the population mean? Justify your answer. So if we go back up a second, okay, part 3, we said a stat is an unbiased estimator if the mean of the sampling distribution equals the parameter. So since we've got 12.8 for the sampling distribution mean and for the population mean, we can say, yes, this is unbiased because they're the same. So yes, the mean of the sampling distribution of x bar is equal to the population mean. Okay. And then part E says, suppose we had taken samples of size 3 instead of size 2. Would the variability of the sampling distribution of the sample mean be larger, smaller, or about the same? Justify your answer. So again, if we go back to part 3, as sample size increases, variability decreases. So if we took samples of size 3 instead of size 2, our sample size is increasing, so that means that our variability is going to decrease. So it would be smaller. As sample size increases, variability decreases. Okay, so if we took samples of size 3, this graph would actually probably be a little bit closer, more clustered together than it is with the size 2. All right, so that is all we have for section 7.1 day 1. On the next video, we're going to be talking about section 7.1 day 2. Still going to be talking about test scores, but in this, instead of having a class of size 4, this time we're going to be looking at a full class of, say, like size 30 and trying to calculate a little bit more with that.